Okay, so my talk is bringing fire to the volcano, or more descriptive, rendering Galaxy on Fire 3 Manticore with Vulkan on mobile devices. And that pretty much describes what I'm going to talk about. So I think last week we launched our game on the Google Play Store, and it's running on Vulkan. So it is possible to release the game using Vulkan, and it's actually working fine now. We also have an OpenGL version, but I won't talk about that because, well, that's not the topic for today. So there's a lot of high-quality content out there on how to get Vulkan running and how to do synchronization and all of that stuff. But I'm not really going to talk about that again. I will just talk about what we learned and what our experience was when bringing the game to Vulkan on mobile devices. Okay, so but first, why am I here anyway? So I'm the head of core technologies at a company called Deep Silver FISHLABS. And FISHLABS is basically the mobile studio of Deep Silver. So we do have our own in-house engine, which is the Abyss engine. And so I'm the lead of that team that basically works on the tools and the engine for our games. So in 2012 or 2013, the start is not that clear, we started working on a game called Galaxy on Fire 3 Manticore, which is basically the next iteration of our Galaxy on Fire IP. And we started focusing on iOS first, and when in 2014 Metal was released, we also jumped on that bandwagon and basically only released with Metal on iOS in the beginning. So that means we now had, because, well, Metal allowed our artists and also allowed our artists a lot more freedom and also made it possible for us to render lots more stuff. We ended up with having something like 1,500 Drawcalls in a number of scenes. So when we now tried moving to Android and were using our OpenGL renderer, we of course had a problem because this was way too many Drawcalls and way too slow. So luckily by then, in 2016, we got Vulkan and we started working with that. So as not everybody might know the game and maybe has not played the demo I had over in the other room, I now... So I'm going to talk about basically two things now. First, I'm going to get into some details on our implementation of our Vulkan renderer. And then in the second part, I am going to talk about what we learned along the way, all the different problems we had, and what maybe might you help then when you try to get your Vulkan renderer on Android running. So our implementation of Vulkan is, I think, more pragmatic than perfect. So we basically tried to ship the game in time, which more or less worked out. So we are not really using the fanciest Vulkan features. We don't have any parallel command buffer generation or not using reusing command buffers. We don't have any custom allocators, nothing like that. But what we have works well enough for our use case. So first to put this into perspective, I hope you already have some kind of rendering setup where you are able to support different graphics APIs. This is what the setup looks like for us. You have the gameplay up there, and then we have the API-independent stuff, what we call render pipeline. This is what does all the culling and sorting and calculating and generation of uniforms. And then we so far had the OpenGL renderer implementation, which also did the ES part, and we had the Metal renderer implementation. And of course, what's new now is the Vulkan renderer implementation, and that's what we're going to talk about. So in there, you have the normal setting of uniforms and textures, binding of shaders, and of course, the emitting of actual Drawcalls. And most of these things come with their own unique challenges when you try to do Vulkan, as we already heard today. So first, let's talk a little about descriptor set bindings. This is quite a thing that's unique to Vulkan, and that you, for example, don't have it's not a challenge with Metal, for example. So basically, a descriptor set is a group of bindings, right? So you have to use them for your uniforms and for textures, and for these two things, we actually have two different solutions. So let's first talk about uniforms. We have one descriptor set per shader, because the descriptor set is basically influenced by what uniforms you have in the shader. And that would mean that now if you wanted to use the descriptor sets, the challenge is that you can't really change them while the GPU is still using them, which what we already heard today. So our solution to this is that we use the dynamic buffer offsets. This way we can reuse the descriptor set in subsequent drawcalls and can encode the offset into our uniform buffer while emitting the drawcalls. So this, as the downside of that, we have to use one very big buffer for all our uniforms. So all our objects and all frames that might be in flight go into this one buffer. So we have one very big buffer, and I think our in-flight frames are limited to 4. So theoretically, we have a maximum number of objects we could generate per frame, but practically this is not really a problem because we just choose the uniform buffer big enough in order for this not to ever happen, that we run out of space in our uniform buffer. So as I said, for textures, we have a different solution because we can't really use the dynamic offsets here. But what our problem here is that our API basically accepts arbitrary shader and texture combinations. So in one frame, you could use one shader with one texture, and then the next frame with different textures. So here you would also have to update the descriptor sets. What that also means, as I said earlier, for the uniforms, that means you would have somehow to manage this, and that would mean barriers or fences or tracking what is still in use by the GPU. So what we instead use for our textures is that we try not to update them, but we try to use them, reuse them instead. So that means that we have a cache where we have as the key the shader and the textures that are going to be in the shader, and then put the descriptor set into this cache. So that means that for most of the frames, we have a hit in the cache, and we don't have to update any descriptor sets. We also tried updating the descriptor sets on the fly. So each frame, tried the managing and then updating them just before the draw call, but this ended up being way too slow on Android. So I think it was like doubled basically our generation of draw calls, or the time used for that. So we are now caching it. Next is the management of graphics pipeline states or render pipeline states or pipeline states in general. So with Vulkan, you can't really use the shader directly. You have to use the pipeline states because a lot of things go into these. For example, the vertex layout, the shader, the format of the render target, the raster, and the blend state. And somehow this is, well, for us, this is not really a resource, so we don't load something from the disk to create a pipeline state for that, but it's more something that happens implicitly. Once you try to render into a render target, you are going to need a pipeline state that can render into this render target. So it's very difficult to pre-generate all the pipeline states because that will be way too many and it is quite slow. And also you might not even know all the pipeline states you are going to need. So our solution for this is that we, again, create a cache on our side. So we take all the inputs that we have on the left side and put basically all the pipeline state objects that we have for one hash into a map, and then retrieve it later if it's already available. So if it's not being compiled yet, we are going to compile it asynchronously. That means an object might be missing for a frame, but normally this doesn't happen because we try to pre-warm the cache. So as soon as we've loaded a complete model where we know the shader and the other inputs like the raster and blend state and the vertex layout, so the mesh is loaded, we try to pre-generate, after all the pipeline states for all render targets that we currently know. So if we weren't doing that, we would have a lot of objects just popping into the frame. Because we try to pre-generate them, that normally also means that we have a cache hit in this case, and we don't have to do it on the fly. But we still have the fallback of doing it asynchronously if a pipeline state object doesn't exist. Then what's also different with Vulkan is that you have to think about your asset pipeline. Actually, one of our asset tools guys is today here. Maybe you've already talked to him, so if you have any questions about that, you can talk to him. But with Vulkan, you cannot use any source shaders, so you have to pre-compile your shaders. What we use is Google's ShaderC, and it translates our GLSL code into SPIR-V. And this has, of course, the advantage that we can reuse our GLSL code and don't have to write any specific Vulkan shader code. So we can share that code between OpenGL and Vulkan. And also one other thing is that you have to be careful is that you don't have any shader reflection. So normally what we did was that when we loaded a shader, we asked this shader what inputs do you need, what uniforms, and what textures do you need. But with Vulkan, you can't do this. So you have to also find a solution for that. You could bring your own reflection data. If you already precompiled the shaders, you could also generate some reflection data at some point, at that point, and then load it when loading your shader file type with that. Or you could do what we are currently doing. We are using SpearV cross. So we precompile the shader and then load it at runtime and then use SpearV cross in order to examine the SpearV code and to figure out that way what uniforms and textures go into it. And I suppose if you had very simple shaders, you could just assume that it has specific inputs and that you can just use them with the shader. Okay, so far about our implementation. Next, I'm going to talk about what problems and issues we encountered and what learnings we basically drew from our bringing of the Vulkan renderer to Android. So we first started implementing on Windows on an NVIDIA GPU because, well, the tools are easier to use on Windows and it was also quicker to iterate on Windows. So only after doing that, we started moving the renderer over to Android and fixing all the problems we found there. The initial implementation took one developer roughly 2 months, but as I said, when moving to Android, there was lots of iteration going on and lots of different devices and lots of different problems that we had to deal with. So what comes now is basically an assorted collection of the stumbling blocks we hit and what we did then to avoid them or to fix them. Maybe this might also help you. First, what we learned is that you have to pay respect. You have to pay respect to the limitations and boundaries and properties that the driver or the Vulkan implementation gives you. So with Vulkan, you can query lots of things and ask for lots of things if they are supported or not and what limits they have. And one problem we hit here was the maximum allocation count. As we also earlier heard today, there is a maximum number of allocations you can do. And as it turns out, on some mobile GPUs like the Adrenos, you can only do 4,096. And with all our shaders and render targets and vertex buffers and index buffers and uniform buffers, we were actually hitting this number of allocations. So we had to redesign how we, for example, create our vertex and index buffers in order to have them in the same allocation and not in separate allocations. Next was the memory alignment requirements. So you can get from the device, you can get the min memory map alignment, which is an alignment you have to respect. And then you can also, for specific buffers, you can call vk get buffer memory requirements to get the requirements, the alignment requirements for the buffer. And then it's sometimes difficult to figure out which alignment you have to use after all. So in some cases, we actually had to use the maximum of the 2 alignments in order to have the proper alignment for our uniforms. What you'll also want to do is, what we also heard today, is check the API version. And I'm going to talk a bit more about that later, because it might not be a Vulkan implementation version that you support at all. Then we have different texture compression formats. So a Vulkan implementation has to support either ETC2, ASTC, or BC texture compression. And if you want to support all the devices out there, I guess you might have to ship textures in all of those formats. What's working for us so far is that we ship textures in ETC2 only, and that seems to work on basically all devices that we at least support. I guess due to it being required by OpenGL ES3, that might make sense that all the devices support it. Then you have different frame buffer formats. So it could be that your GPU supports RGBA or BGRA. You have different depth and stencil formats, and they might be combined or not combined. So you should also check that, what your Vulkan implementation wants before you create your buffers. And then last, you have the composite alpha flags. That flag determines how your window is composited with the rest of the desktop. And this is also something that's different between Windows and Android. And you should query what you have to use. What we also learned is that validity doesn't imply correctness. So this is about the validation layers, and I'm going to say it again. They're super useful, so you should really use them, and you should also make it easy to enable them. And if something goes wrong, that should be the first thing you should do, check if the validation layers find something. But what we also learned is that you actually have to load them in order. In the beginning, we didn't know that. So there's a recommended order of validation layers, and if you don't load them in the correct order, then they might not be able to work at all, or just not give the correct error messages. Also, the validation layers are still work in progress. So you should, if you want the latest checks, you should get them from GitHub and compile them yourself, and not use any pre-compiled ones from anywhere. Then the validation layers are also in a way device-specific because they also query the device properties. So if the validation layers don't report a problem on one device, doesn't mean that it won't report a problem on another device. So that was, for example, the case with our maximum allocation limit, because it was also checking the device limit. And so we didn't have any problems on devices that allowed more memory allocations than 4096. And the last thing is here that's actually a bug that we already reported, but I have to say it anyway, that on some devices we couldn't load any validation layers just because after we integrated the Google Play libraries, the driver was now looking in the APK for the Google Play libraries. So there's some problem going on there, but I hope it's going to be fixed soon. Next, I have another video. No. Yeah. To do that externally as well. Okay, you can already see it. So maybe someone has an idea what's going on here, what this might be. So in some cases, stuff not being cleared, but here it's more weird. So depending on how the ship is rotated, it's rendered correctly or not. Yeah, and again, stuff not being cleared. Anyone know what this might be? I will tell you. Oh, I have to close it. So it's the dreaded VK error lost device. So, and this means, or device lost. So that means that you did something wrong. And this might have a lot of different causes, but it generally means that something went awfully wrong and that the GPU or driver had to be restarted because it just was that bad. And this is also super difficult to debug because, as we saw earlier, everything is basically asynchronous. So the driver is already asynchronous, and then you have the GPU that's doing asynchronous stuff. And then if the device actually had a problem, it will be reported later at some point when you call some unrelated function, and then you get the VK error device lost. So some examples, there are, of course, a lot of things where this can happen, but for us this happened, for example, when we had uniforms that had any values that didn't make sense. It happened when we were sampling from textures that we never assigned anything to, so we didn't update the descriptor set for the textures, and also, of course, with all the synchronization issues that you can run into. What we also discovered is, we've also already heard that today, that the drivers also still have issues. So sometimes you have to accept that there is something you cannot fix and that you might have to work around because, well, it might be the driver's fault and you can't change it at all. So specifically for us, this happened on the Adreno GPUs where we had two problems. Of course, this may also have been our fault in the end, but it was very clear to us that when we worked around these two things or changed how we did it, was that the problem was then fixed. So we are currently assuming that these were driver bugs, or still are driver bugs. So for example, when creating the layout for our uniform descriptor sets, we have up to 4 uniform structs in our shaders. And we were basically creating the layout bindings in a random order in the array that we were passing in to create the layout. But we were still assigning the correct index in the binding index in the layout binding. But somehow the driver seemed not to care about the index we were specifying, but was taking the index in the array we were supplying to the layout binding instead. So once we sorted our layout bindings in the descriptor set layout, it started working again, and we had the correct uniforms as opposed to before we had just the wrong uniforms being assigned to the wrong structs. And we also used some dynamic pipeline states, specifically for the viewport and the stencil rectangle. We marked that as being dynamic pipeline state, and because, well, theoretically, our API allows people to set it like that. but this also caused some problems on the Arduino GPU. Some objects were flickering, and it was especially bad when you're pulling down the system menu from the top of your device. Then we had just flickering on half of the screen and stuff like that. So when we disabled the dynamic pipeline instead, this was working again. Luckily, this didn't really cause any problems because it was not being used anyway. But there are not only bugs in the drivers, but also they behave differently. And I have 3 examples of that here. So one example was that for our particles, we were generating the index and vertex buffers at the same time. So we were mapping one buffer twice, basically. And this is wrong according to the spec, but it was working on a lot of devices anyway. But then on some devices, it didn't work. And when we enabled the validation layers, we found out that this is not actually something you can do. And then we had to rework how we generate our vertices and indices. Another thing that we forgot was to specify the external dependencies for our render subpasses. So that means some things were not done rendering in time before we started rendering our next render pass. And this would very, very seldomly on some devices lead to one black frame. And after we specified the external render subpass dependency, this was fixed as well. And then what we also did was, for our 2D textures, we were setting the depth of the texture to 0, which, well, it happened, might not make sense, but according to the spec, it has to be a depth of 1 for 2D textures. But this was working anyway on a lot of devices. Yeah. But it was fixed when we set it to 1 then. And now I have 2 very Android-specific slides. The other stuff might also apply to Android. But yes, that's also something that we've already heard, that Vulkan can be available on Android 6. But it's a bit more complicated because it was only added properly in Android 7 or API level 24 or Android Nougat or whatever you want to call it. But there are some devices, specifically the Samsung Galaxy S7 and the NVIDIA Shield tablet, where you can get Vulkan running on Android 6. But, well, you cannot really depend on the header or the library being there, so you have to load the Vulkan SO dynamically at runtime. And for that, we are using a Vulkan wrapper that's actually part of the Google samples, and this does all the, well, typing-intensive stuff for us, like loading the library and getting all of the function pointers out of it. And that way, we can also support Vulkan on the Android 6 devices. But also, just because one device supports Vulkan on an Android 6 device, doesn't really mean all of them do. So what we found that some devices were then reporting an API version of 0.0.1, which didn't even have a swap chain extension or support for validation layers. So in that case, we are now just saying, well, we don't support Vulkan on this device. And other devices were giving us or telling us themselves that they were not compatible with us. So in that case, we are also saying, well, Vulkan is not supported on this device. Okay, and to what? Oh, yeah, another Android-specific thing, right? So with Android, you also have the life cycles. So anytime, or yeah, at any time in the game, you can basically press the home button and pause the game, and then later come back to it and resume it. With mostly anything Android, you have to handle this somehow. And there wasn't really any documentation on it. So what we found out was that your surface is destroyed in that case, and it is also being recreated. And for Vulkan, that means that you are going to have to recreate your swap chain and all of its frame buffers. But what you cannot do in this case is that when you call vk create swap chain KHR, you cannot supply the old swap chain as into this function because that swap chain is already invalid because its surface has been destroyed earlier. Okay, so to conclude this talk, I've brought some numbers. First, about how many lines of code this actually took us to implement all the renderers. So first for OpenGL, which was also our first renderer, it's maybe a bit too small to read, it's 3,100 lines of code. Then we have our metal renderer at 3,400 lines. And the Vulkan renderer is a bit higher at 4,400. So if you compare OpenGL and Vulkan, it's basically an increase of 40% lines of code. This might be just a rough measure because, well, maybe we implemented stuff differently, but after all, the implementations basically have feature parity, and it's something that you already see when you look at Vulkan code. It's just more explicit in what you have to do and what you do and what has to be done. And I also did some profiling. So one specific scene where we had about 1,400 Drawcalls, and I did this on 3 devices. Yeah, let's just look at the OpenGL ES numbers. So for the Nexus 5X, it took us just to generate the Drawcalls about 70 milliseconds. On the Galaxy S7, it was about 32 milliseconds, and on the Google Pixel XL, it's about 33 milliseconds. And if we now take the Vulkan implementation just to generate the Drawcalls, it's at 26 milliseconds on the Nexus 5X, at 11 milliseconds on the Galaxy S7, and at 8 milliseconds on the Pixel. So if you now divide these numbers by each other, you get a 3 to 4 times speed increase when comparing OpenGL ES to Vulkan in this case. So if I had to boil down this talk to 3 main points, it would be if something is slow, try to cache it. Vulkan does indeed improve performance, as we saw on the previous slide. And you should expect a lot of work when taking your renderer from Windows or from another platform to the different Android drivers and devices, because they are all very different. And that's already it. So any questions? You can ask them now or later, or send me an email.
Approximately, how long it took to implement Vulkan for PC and then for Android? You said you started on the PC, right? Yeah,
it was about 2 months for one developer on the PC, I think. And then, well, Android is difficult to say, but because at that point we also started doing the OpenGL version. But it might have been another 2 months.
Okay, thanks.
So I just wanted to inject that I don't actually know if the spec says whether you can map the same buffer twice. I suspect it does say it somewhere. And so if there's an inconsistency there, I'm interested enough, I'll go find out. But you can definitely go to GitHub and create a bug in the conformance test that says, hey, we noticed some implementations allow this and some don't. What gives? Yeah. And it'll eventually get into the test.
Okay. Yeah, I think it was actually covered by the validation layers.
Oh, validation did catch it, so it is an error, or it is a validity error. Okay, cool, thanks. Yeah, so that's an unfortunate fact about Vulkan is that since if you break a validity constraint, one of the possible legal behaviors is it might work. Yeah. And we just can't, we can't afford to enforce that it doesn't, because then we would have to check for the error on some implementations.
So not a particularly technical question this time, but several people have mentioned the problem of sort of getting games to run on many different devices. Is there like is there a central pool of devices people can use to try things out on?
I'd like to know about it, but you can reduce the complexity a little by looking at the SoCs and the GPUs specifically. So if normally you have the same problems on Adreno GPUs and the same problems on Mali GPUs, and then, I don't know, the NVIDIA GPUs might have a different problem. So the NVIDIA mobile GPUs are very similar to the desktop ones.
Yeah, because Microsoft used to have a thing where they brought the developers and the chip makers together to try and iron out the bugs.
I don't think there's.
Maybe we should start one.
Yeah, you can't map things twice. I just checked.
Any other questions? Nothing online. There are people online, I think. Okay, thank you, Johannes.